recording. You're going to be looking at an analgesic drug. So you're going to be given an unknown capsule, and you get to isolate the drug inside it and purify it to roughly the best of your abilities. Okay. So general steps of any experiment, and this one's slightly modified. You should prepare for class, you should prepare for lab, that kind of a deal. You'd get into class, run the experiment, run the reaction. You'd isolate whatever products you were trying to get out of it. You'd identify whatever it was, and then you could calculate a % recovery. Okay? As far as what you're dealing with in this case, just the ones that are kind of bolded, those are going to be the ones you're going to deal with. So it's a repeat of pretty much all of the techniques except for IR spectroscopy, which is slightly new. And then we're also going to introduce you to some new equipment as well. That's pretty much what is going to show up on the next slide, so we'll just chip that because it's pictures. So you'll be given some capsule or some unknown tablet, which in theory will not say on it what it is. If it does, you just get to ignore that and do the lab anyway. Okay? So we'll crush up that tablet. Why might we crush the tablet? More surface area, which means we can increase the interaction with our solvent. Okay, so we can potentially get more compound out of that capsule. You'll end up extracting that in methanol. The old slides, and I don't think those old slides are posted anymore, showed a filtration. You're not going to deal anything with filtration, so no Hirsch funnels, anything like that. It'll be nice and simple. So you'll shake it up in some methanol, centrifuge, and collect the liquid. You'll do that twice, and then you will run that liquid through a simple column, okay, to purify, in theory, your analgesic. At that point, you'll have your pure compound with a bunch of solvent. Okay? You need to isolate the crystals of your compounds. You need to get rid of the solvent. It's the easiest way to get rid of most solvents. Anybody? Does that get rid of the solvent? Evaporate. Okay, it is on there. So what we're going to be doing is evaporating the solvent. We're going to use some fancy new equipment, which in theory should make it go faster. It's called the Centrifan. We'll talk about that in a little bit. The end of that process, you should end up with solid product. You'll isolate, or you'll take that solid product and do an identification process on that. Okay, so again, another figure to kind of show what's going on with this. You'll take your solid, you'll mix it up with 2 mils of methanol, centrifuge it, you'll get that white pellet at the bottom of the capsule. You'll take the methanol off, okay, and set that aside. You'll add a fresh batch of 2 milliliters of methanol. Why might we do this twice? There's no column at this point. This is still in the centrifuge tube. Why would I add methanol and shake it up twice? What's that? Yeah, we're just trying to maximize the yield of the product coming out of the capsule. Okay? So we just want to do that twice to make sure we get as much as we can out. You'll take that 4 mils and you'll run that through your column using alumina as your stationary phase and I think methanol as your solvent. Okay? At that point, again, you've got your solution that has your active ingredient in it and methanol. So you need to get rid of the methanol, and that's where we'll use what's referred to as the Centrifan. Okay? So it is similar to a centrifuge, sort of, but it helps speed up the evaporation process, and it also gives us some other additional features. Okay? So why even deal with special equipment? Okay? How could you typically evaporate solvent? It's the easiest way to do it. Just heat it up. So we could just put this on the hot plate and boil off our solvent. Okay? What's in general a bad reason for, or a bad idea? Why is that a bad idea? Let's try that. You could potentially see your solute evaporating, but in most cases you won't see that. It will stay as a solid. It might turn into a liquid, but the odds of it going from the solid to the liquid to the gas and actually losing it are pretty slim.
You breathe it in.
You've now exposed yourself to organic solvents. Okay? You've turned those into a vapor. Those are now in the gas state. You can potentially breathe that in. That is a possible hazard. Okay? So what we want to do is prevent that from occurring. That's what the Centrifan will do. So it's going to speed the evaporation process. We'll talk about that a little bit. And then you no longer lose that solvent to the atmosphere. So it's Safety-wise, it's better because you're not breathing it in. And then further, you can collect and reuse that solvent. Okay? So you spent X amount of dollars on that solvent. Now you can reuse it or use it multiple times, get more value for your money. Okay? This instrument can hold 6 samples. We ask that when you use it, you keep it fully loaded. Okay? That it is filled with all 6 samples. Otherwise, half your class is going to be really upset when you run just 1 sample in it. Okay? Because they have to wait for you to finish. Your samples will get loaded into that bottom part. There's a little white area there. You'll get special vials that you'll put inside that. Okay? Once it's fully loaded and balanced, we'll go ahead and close the lid down. Okay? And then kind of lock that closed. Once it's closed, what's going to end up happening is it's going to spin. That's where we get the centri or centrifuge action. So as it's spinning, what it's trying to do is wash solvent up onto the sides of the container. Why would that be important? What does that do? Kind of related to heat getting in, but not quite. Maximizes surface area. Okay? The more surface area there is, the faster it'll evaporate. Okay? So as we spin it, we'll maximize that surface area and increase our evaporation rate. Okay? The other thing that it does while spinning is it's got propellers in it that causes a fan action. So it's actually going to be blowing air out the back end. So as the solvent evaporates, it blows that now solvent-rich air out the back of the instrument. So if you look at the instrument, you'll find 2 little attachments or hoses in the back. One of those hoses, which is the output, goes over to this glass thing on the side. Okay? And if you look very, very carefully underneath what I'm now drawing over, there's a little finger, is what we would refer to it, aiming down into that glassware. That will be filled with something very, very cold, either ice water or dry ice and acetone, so something that's ridiculously cold. Okay? What happens when our vapor gets near that cold? It liquefies. Okay? And it will drip and collect down in the flask underneath. Okay? So now we've collected it. But where does the rest of that air go? We've got a valve out the top, which will then come back into the instrument. Okay? What's special about the air coming back in? What does it no longer have in it? The solvent. Okay? Why is that important for us? Well, if we look at the evaporation process, let's see if I can draw it on here. If we take a beaker and we've got liquid in it, what's happening as we evaporate? Okay? We're going up into the gas state. Well, what does that gas do if we're in an enclosed system? It can also return to the vapor, right? So it's an equilibrium. Okay? What's happening when we use the Centrifan? That gas is formed, and then it goes somewhere else, and is collected and removed. Okay? So as our reaction's occurring, what's happening to the gas as it's formed? It's being removed. Well, this is an equilibrium reaction, so what ends up happening to the vapor, or your liquid? Should have written that better. What does your liquid do according to our equilibrium principles? Le Chatelier, it needs to replenish that gas. Okay? So we keep evaporating off until eventually what happens? There's no more liquid to evaporate off. Okay? So it drives the equilibrium, and in theory we'll speed that up, allow it to happen really, really fast or faster, but we'll see how well it actually works. Okay? This piece of equipment is new to the TAs as well. They'll be getting trained on how to use it Friday. I guess that's tomorrow. So in theory they will know how to use it, and if it works, you guys will be using it as well. Okay? If it doesn't work, we can resort back to the old technique of just adding heat. Okay? And that will work as well. So we now have our solid crystals, so we need to identify our compound. How can we identify the compound? We could obtain a melting point. So we've got 3 possible analgesics that you can work with. Okay? So we can just run a melting point. We got 3 very, very different temperatures. Okay? So that's nice. We've got access to those. We won't have any real confusion there in theory. Okay? But what would you say is your result if, say, you got a melting point of 118 to 125. So first off, it's impure, but what's your goal for this whole lab? To identify the compound. Okay? We don't have any other techniques after this beyond purifying it. So how could you potentially identify your compound with that melting point? So we could move to a different technique for identification, and that will help us out. But let's say you don't have it. Okay, so you could mix them if they were pure, but your compound, according to your melting point, is already impure. So even if you added it to something else that was pure, and it was the same compound, your compound to start with was still impure. No, it still comes back to the melting point. Still back to the melting point. What do you think your compound is? Could it possibly be ibuprofen? Why not? It's too high, so we could cross that one off our list. Okay? Could it be acetaminophen? Okay, it's lower and it's broader, so it could be potentially because of that property of it being impure, right? But how much lower is it? A lot lower. Okay? So we might predict or guess that it's probably not acetaminophen because it dropped way too much, okay, or way more than we might expect for an impure solution. Okay? So we'd be kind of tied between those two compounds, acetylsalicylic acid and acetaminophen, but we would probably lean towards it being acetylsalicylic acid because it does have that depression, but it's not a ridiculously large depression. Okay? Does that make sense? Okay. So we do have other techniques just in case this occurs. We can go through and do TLC. How are you going to use TLC to identify it? Okay. You can just spot it on a TLC plate against all of your known standards and compare the RFs. What if the RFs are similar? We could run a co-spot. Okay. It's not officially in the procedure, but you're probably getting points for identifying your compound correctly. May not be a bad idea if the RFs are close to run a co-spot just to make sure. Okay? The very last technique is IR, and it is the most sketchy as far as our equipment goes. Okay? Which we'll talk about in just a second. So again, all of the individual parts. Okay? You've seen melting point. You should in theory know how to do that. You got all those lovely pictures. TLC, again, in theory, you should know how to do that. And then IR. So this is our new portion of this. We're going to look at it in a lot more depth when it comes to the quiz week. We will meet for recitation during the quiz, and that recitation is going to be discussing IR spectroscopy, okay, which you'll probably also see in your lecture. But when we talk about it in recitation, we're aiming more for the practical uses of IR as opposed to the theoretical uses. Okay? So at this stage in the game, we're going to get into a lot of detail about it, but what you ultimately really need to know, okay? IR is infrared light, okay? And what we're going to do is aim that light or energy at our molecule and see how our molecule responds to that energy, okay? Just so happens that every bond has a characteristic energy associated with it, okay? That energy associated with it happens to match infrared light, okay? Or be very close to it. So what we end up doing is scanning our compound across the infrared region, okay, which you'll see down in the bottom of this, okay, 800 to 4,000 inverse centimeters. And wherever our sample absorbs that light, we see a peak. When we're dealing with IR, we're looking at percent transmittance. So our peaks are actually what most people would consider valleys, okay? So all of these little jagged things aiming downwards are our peaks. Okay? Each of those represents some kind of bond found within the structure. Okay? Well, what's different between each of your compounds?
Bonds.
The bonds, which means what would you expect for the IR spectrums for each of those compounds?
They should be different.
They should be different. So what you're going to be expected to do is to use the IRs, our standard IRs that should be posted on Blackboard, and you'll compare your IR, your obtained sample, to those standards and try and match it that way. Okay? A couple things that I'll also address on this. When you deal with this, you will probably be told that this whole region here that's now boxed in, you won't have to analyze in lecture. Okay? There's a lot of important information in there, and it also tends to be a lot more difficult to interpret. Okay. Lots and lots of signals. It is typically referred to as the fingerprint region. Any ideas why it might be the fingerprint? It's very specific to an individual compound. Okay? So if you compare that region, everything should match up perfectly. If it doesn't, it's probably not that compound. Okay? Much like we can identify each other based on our fingerprints. Okay? We just don't do it. Okay? One thing to question about that. What if you have an impurity? Would you expect that impurity to show up in the IR? Yeah, the impurity has bonds. Okay? Bonds will show up in the IR. So if you had an impure sample, would you expect it to exactly match? Probably not. You'll probably see some other signal show up in there due to impurities in your sample. Okay? Just be aware of that. You're trying to overlap it as best you can, and it should be pretty close, but we'll see. Very last thing is calculating your percent recovery. You should be familiar with how to do this. The hardest part of this is going to be knowing the initial amount. We're now telling you that, so you don't have to guess at it. If you're getting, or if you identify it as acetaminophen, 500 milligrams is what you started with. Aspirin, 325, ibuprofen, 200. Okay? So that is pretty much the whole lab, which brings us to the group activity. So a couple things that I want to address before just giving you free rein on this. The intent of this group activity is to get you thinking about the procedure. Okay? Whenever we've got quizzes, everybody asks, well, what questions would you ask? Well, what we end up doing to figure out questions is we look at each individual procedure and we say, crushing the tablet. Why did we make them crush the tablet? Okay? Oh, there's a perfect question. Why did we crush the tablet? Well, what was the answer you guys gave me? Increase the surface area so we can maximize our interactions. Okay? That's how we generate our questions. We go through line by line and say, what was the goal of this step? Is it something important procedurally? Is it something important experimentally, theoretically? Okay? It's addressing each of those individual issues. Okay? So this works for you as far as studying for your quizzes, because in theory you should do this with all of your labs. Okay? We're forcing you to do it on this one as kind of a simpler one, so you get a better feel for what's happening and what you did with the previous labs. Okay? So the intent is to go through, label each of these with what the ultimate goal was. Okay? Based on the key that was sent out to me, apparently only me, first off, the answers for this are supposed to be short and simple. We're looking for a sentence explanation. We're not looking for paragraphs. So if you're writing paragraphs, it's not necessarily wrong, but you're probably putting a whole lot more effort into it than we're expecting or asking for. Okay? To top it off, if we shift all the way through this, the intent was for it to match your lab so that you can actually figure out what's going on and start thinking about it a little bit more critically. But if we take a look at questions 12, 13, and 14, okay? Question 12, why is it essential to evaporate methanol quickly if you are isolating the aspirin? Anybody know? I haven't said it yet. I will say it. Okay? You probably don't know because you know nothing about the chemistry of these molecules. Okay? What's happening? Methanol can react with the aspirin. I'll write up the reactions on the board so you can see what's going on with that. It's not explained in the lab manual. It's not explained in our slides. Okay? To top it off, question 13, cooling the heated solution. How many of you have already read the procedure? Really? Nobody? Really? Okay. For those of you that at least vaguely scanned it, do you cool anything in this experiment? No. Okay? These questions were written from the old lab. We've modified the lab and we've got to adjust these. Okay? So let's think about it from a different perspective. Why would you cool any heated solution? Bless you. To get crystals. You cool so that it precipitates, so you've got crystals. That's why you'll cool solutions. Okay? Filtering the solid with a Hirsch funnel. What did I say at the very beginning? We're not filtering with a Hirsch funnel. Okay? So again, let's go back to why would we ever filter with a Hirsch funnel? To separate Solvent is very specific. I'd go even more general, but that's right. Liquid from solid. Okay? That's why we filter. We're just trying to separate those two things apart. Okay? Everything else is fairly well, at least interpretable. I noticed there is a typo. Question 6 says repeating steps 2 through 4. That should really be 3 through 5. And then question 4 and 5 are pretty much the same thing. Okay? So whatever you write for 5, write the same thing for 4, and you'll be covered. Okay? If you've got questions, please raise your hand. We'll come around and answer those to the best of our abilities.